In this section, we're going to look at the fairly abstract concept of a vector space. So a vector space is a set, usually denoted with the letter V, along with an operation, usually written as plus, called vector addition. And a second operation with the set of real numbers called scalar multiplication that satisfies these 10 axioms. And these are detailed in the beginning of section 4.2 of your linear algebra book. These 10 properties here. To really get a feel for this is, as I mentioned, a fairly abstract concept of vector space. It pays to see a couple of examples and a couple of non-examples. So this first example we're going to show all the details on. This is the set of polynomials. These are polynomials with real coefficients. So before getting into this, let's just remind you the formal definition of a polynomial. P is a polynomial in P if it can be written as a combination of powers of x, where these are allowed to be integers, and this is a finite sum. It stops at some point, and that point is the degree. So this is our definition right here. We have we add and distribute, multiply polynomials just like we're familiar with, foiling, combining like terms, that sort of thing. So all the regular definitions of polynomial operations hold in this space right here. We're just going to go through these 10 axioms and verify that this is indeed a vector space. So the first axiom that we need to verify is that this set is closed under addition. So what that means is, so the general gist on showing something is a vector space, what we do is we say let U and V be in our set. And the goal on here is to show that their sum is again in the vector space. So if these two are polynomials, we can use our definition to write these out. So U must be some string of coefficients along with powers of x, and V has its own coefficients and powers of x. So if we add these two together, U plus V, this is the sum AK x to the k plus the sum BK x to the k. And the usual rules of polynomial addition hold here. We're just going to combine like terms, and these have the same power, x to the k, so we combine these into a single sum, AK plus BK x to the k. So this is again a polynomial. This is a finite sum because both of these were finite. There is a largest AK, there is a largest BK. So this is a finite sum. These are all real number coefficients of x to the k, so it's again a polynomial. So we have that U plus V is also a polynomial. So the first axiom holds. So next up, axiom number 2 is that addition is commutative. So the idea here is we'll take two vectors in our vector space, and the goal here, I'm putting this goal in parentheses. When you do these problems, you don't need to explicitly state this out. This is just to make sure you understand what we're going for on all this. So the goal on this is to show that U plus V is the same thing as V plus U. That the order of addition doesn't matter for vector addition in order to be a vector space. So if we let U and V be polynomials, again we can just use the same setup here. Then U must have some coefficients and powers of x, and V must have some coefficients and powers of x. And if we take U plus V, well, we saw from above how this is defined. This is the sum of AK plus BK x to the k. I'm just sort of shortcutting to this last step that we showed before. Now AK and BK are real numbers. And we know real numbers are commutative under addition. So I can just switch the order on these and write this as bk plus ak x to the k. And this sum I can split apart as the sum of bk x to the k plus the sum of ak x to the k. So you can think of sort of like undistributing here. And this is the same thing as v plus u. So I have that u plus v is the same as v plus u, and we've got it. That was our goal on this, so we know that the second axiom is satisfied, that this operation is commutative. Third step. The third axiom on here is to show that the addition operation is associative. So what we'll do here, now associativity is the moving around of parentheses. So we're going to start out with 3 vectors in our vector space. And the goal here is to show that if I add the first 2 together and then the third, this is the same as adding the last 2 and then the first. Now I'm not changing the order here, u, v, w, u, v, w. The order is the same, it's just that I'm deciding which addition operation is coming first. So, like before, we'll write out what these mean. So u we can write as a string of coefficients and powers of x. V is likewise, those are possibly different coefficients, bk x to the k. And w has its own string of coefficients and powers of x. So let's start out with this left-hand side of our goal, u plus v, then plus w. So if we take u plus v plus w. Now u plus v, we actually did this above on each of the previous problems. We know that this is the sum of ak plus bk x to the k. And this w will sort of come along for the ride. The sum, let me just for emphasis on here, this w is the sum of ck x to the k. So we've done here, we've taken the u plus v, and we've added that together first, and then we've tacked on this w. And now we can combine like terms here, and this will give us the sum of ak plus bk plus ck x to the k. And now since real numbers, addition of real numbers is associative, we can shuffle the parentheses inside this sum as ak plus bk plus ck x to the k. So what we've done here is we've decided instead of adding a and b first, we'll add b and c first. And this sum, as we did before, we can break apart as the sum of ak x to the k and the sum of bk plus ck x to the k. And this is just the same thing as u plus this last part right here is the definition of v plus w. So we've shown that we can just shuffle the parentheses around when adding up these polynomials. So our third axiom is satisfied. So we've shown that addition is associative. The fourth step is to show the existence of a zero vector. So what we'll do here, the zero vector is usually obvious given whatever space you're in. This is going to be the thing that has 0 everywhere, whatever that means. So usually we reserve a special symbol for the zero vector. We usually use this Greek letter zeta. And I'm going to define this to be the polynomial 0 x to the k. This is the polynomial all of whose coefficients are 0. And then the goal here is to show that if I take this and I add any polynomial u, it doesn't change. So let u be any polynomial. Then I know I can write it as the sum of some coefficients and powers of x. And if I take zeta plus u, well, this is the same thing as the sum of 0 x to the k plus the sum of ak x to the k. And now using our definition of vector addition, this is the sum of 0 plus ak x to the k. And then using the identity property for real numbers, I know that 0 plus any real number leaves it unchanged. So this becomes the sum of ak x to the k. And this is just the same thing as u. So this says that if I add the zero vector to u, it remains unchanged. So we've got our fourth axiom down. We know that it satisfies the zero vector axiom. There exists a zero vector. Part 5, the inverse axiom. So what we have here, we'll let u be a polynomial, and the goal here is to come up with a second vector. Maybe I'll call it u prime. To show that when I add u and u prime, these sort of all cancel out and give you the 0 vector again, the vector that we've actually defined in the fourth axiom. So I guess before I define this u prime, I need to write out what the terms of u are. So u is again our generic polynomial. It's got some coefficients and some powers of x. So let's define u prime. Well, we want it to be the thing that will cancel out with u. So what we'll do is we'll just negate all of its coefficients. So if we were to sum up u and u prime, well, by the definition of addition, I can go and add their coefficients, ak plus negative ak, x to the k, x to the power of k. And then if I combine the coefficients, I get the sum of 0, x to the k, and this is my definition of zeta. So I have that these two add up to give me the identity. Therefore, axiom 5, the inverse axiom, holds. So we've gotten through the first 5. The first 5 all deal with just addition. These are all properties of the vector addition as defined on the vector space. The last 6 involve scalar multiplication on one level or another. So we've done the first 5. Next up, we want to show that this is closed under scalar multiplication. So what we'll do here, the idea is we're going to let c be a real number and u be a vector from our vector space. The goal here is to show that c times u is again in the vector space. Well, to do this, if u is a polynomial, just like we've done on every step so far, u can be defined as the sum of the coefficients and the powers of x. And if we take c times u, well, this is c times the sum of ak, x to the k. And I know that when working with polynomials, one of the operations of the polynomials is multiplication, and we define it by distributing. So we'll distribute this through, and this gives us the sum of c ak, x to the k. And again, these coefficients are real numbers. So, and this sum is still finite. So again, this is a polynomial. So we've shown that our vector operation is, our vector space is closed under scalar multiplication. So step 6 is done. Next up, the first distributive property. Now, when dealing with vector spaces, there are actually 2 different ways that we can have distributing, and both of them have to work. So let's look at the first distributive property. What we'll do here is, now the first distributive property shows that scalar multiplication distributes over vector addition. So what we'll do is we'll let c be a real number, and we'll take 2 vectors in the vector space. That means we can write the first one as ak, x to the k, and we can write the second one as its coefficients and its powers of x. The goal here is to show that if I take, if I take c times this sum, I can distribute this through the that vector addition operation and get cu plus cv. Okay, so let's try this out. Let's take c times u plus v. So this is c times, now u plus v, we've done this before, and this gives us the sum of ak plus bk, x to the k. And as we saw in the previous step, I know that this c can distribute over all the terms because that's how multiplication of polynomials is defined. This gives us the sum of c, ak plus bk, x to the k. Now we can use the distributive property of real numbers to distribute the c through, and we get cak plus cbk, x to the k. We can do the same thing by distributing the x to the k through, and we get the sum of cak, x to the k plus cbk, x to the k. And this we can break into two separate sums and factor the c's out. Not factor the c's out, just break this into two separate sums. Write this as c akx to the k plus c bkx to the k. And this is cu plus cv. And that was the goal on this, was to show that the c scaled, that the scalar distributed through both terms of the vector addition. So we've shown the first distributive property. The second distributive property works the same thing, but it's sort of in reverse. We want to show that if we've got a scalar multiplication, if we've got two different scalars, so if we take c and d to be real numbers, and u to be in our vector space, the goal here is to show that if I take c plus d and multiply that, scale that through to the vector u, this is the same thing as if I sort of reverse distribute the u through and get cu plus du. So that's our goal on here, is to show that scalar multiplication distributes through scalar addition as well as vector addition. So here the c and d are scalars, on the previous one the u and the v were vectors. So we know that scalar multiplication distributes across vector addition. We also want scalar multiplication to distribute across scalar addition. So let's start this out. So u must be a string of coefficients and powers of x. So let's write this out. C plus d times u. This is c plus d times, the definition of u is that this is the sum of ak x to the k. And now this c plus d is nothing more than a polynomial, which is of very low degree, so we know we can distribute this polynomial through the other polynomial, and we get c sum of ak x to the k plus d sum of ak x to the k. So here we're not really doing anything deep, we're just applying the rules of operations between real numbers and polynomials, and we get that this is cu plus du. And that was what our goal was, to show that this scalar multiplication distributed over scalar addition. So we've got the two distributive properties down now. We've got two more axioms to show. We want to show that scaling is associative as our next step. So what this means, so just like in the last one, we're going to take two scalars and a vector. So our vector, we can, as before, write this as coefficients and powers of x. The goal here is to take c times d times u. This looks a little bit analogous to what we had before, although we want to be able to reassociate those parentheses and multiply just one scalar at a time first. So we want to show that we can either multiply the scalars together and then scale the vector, or we can scale by the first scalar multiple and then by the second one. The order shouldn't matter. So let's start out with cd times u. So this is cd times the sum of ak x to the k. So now I can take this cd, and by performing the operations of polynomials, I can just take this scalar and distribute it through. So we can write this as cd ak x to the k. And now I can use the associative property of multiplication of real numbers and shuffle the parentheses around inside here and write this as c dak x to the k. And now we can use the scalar multiplication property and pull this c out. This is c times the sum of d ak x to the k. And this, by definition, this part right over here, is the sum. I pull the d out of this sum and I get ak x to the k. And this is c times du. So just by sort of performing the operations we know with on polynomials, we've shown that c du is the same as c du. So we've got we're almost at the end. We've got our scaling being associative. The last step on here is to show our unit axiom. And that just tells us about the number 1. So if I take any vector in the vector space, the goal here is to show that 1 times u is the same as u. just like the property holds for real numbers, we want it to hold for vectors in our vector space. So u is the sum of ak x to the k. So if I take 1 times u, this is 1 times the sum of ak x to the k. Now we can distribute this, this 1 through the sum using properties of polynomials. And now 1 times ak is the same thing as ak. And this, by definition, is u. So we've got the 10th axiom down. So this shows us that P is a vector space. So as you can see from this, this is a very long process to show that the set you're working with is a vector space. Let's look at some non-examples. These go much faster than actual examples do. So let's for our first non-example, let's take the set of positive polynomials. That is the set of polynomials that only take on positive real numbers as their values. So these would be things like, say, x squared plus 1. This is never negative, as an example. Well, I know it has to say this, that if this is to be a vector space, it must satisfy those 10 axioms. So if we go back to the original list, we just want to find one of these that fails. So if we go through the list, closed under addition, well, if I add positive numbers, I'm getting a positive number. So it looks like this is not going to fail. We're looking for a place where this is going to break down. If we go and look at 0 vector, well, the only 0 vector possible in the set of polynomials is the polynomial that has 0 as all of its coefficients, 0 x to the k. Now this is not positive. It's not negative, but it is not positive. So that tells me that this set we've got right here, this set does not have a 0 vector. So it's not a vector space. So if it fails one of the axioms, then it is not a vector space. Well, that one we kind of cheated our way out of. Let's take one that maybe gets rid of this. Let's say we look at the set of non-negative polynomials. So 0 is a non-negative polynomial. So I know that this set does have 0 vectors. Well, let's go back to the original and see if there's something that we can find to break this, so we don't have to actually verify all 10 of these. Usually things will tend to go wrong under the closure properties, so these are the first we want to look at. If we add 2 non-negatives, we'll get a non-negative back, so the closure under addition is not an issue. Closure under scaling, though, that may give us a problem. If we so let's just take x squared plus 1. So we have a specific element from this set, and let's take our favorite real number, negative 1. If I multiply these together, if I take negative 1 times x squared plus 1, I get negative x squared minus 1, which is not non-negative. So in other words, it's not back in our set again. So that means our set is not closed under scalar multiplication, so it fails axiom 6, so it's not a vector space. Okay, let's maybe look at one more. Let's, as another non-example, let's look at S is the set of rational numbers. These are things like fractions like 1/2, 3/4, negative 2/11. These are numbers that can be written as an integer divided by an integer. So if we go back and check those axioms, rational numbers are closed, they're commutative, addition is associative, 0 is a rational number. If I take a rational number, its negative is its inverse. So if I look at closed under scaling, that seemed to do well last time. Let's take an arbitrary rational number. Not arbitrary. Let's pick 2/3. That's a rational number. And then I can take not r. That is a rational number that is in our set S. And I can take a number like pi. Pi is a real number. If I look at the scaling property, that means I need to be able to take my real number times the element from my set and wind up back in the set again. But 2/3 pi is not rational. So this fails axiom number 6, and this is not a vector space. So the first thing you should always try to do is see if you can go through the axioms and find one for which your set fails. Because if you can find one where it fails, you don't need to check the other 9 axioms. You can just do one and you're finished with the problem. So if you do wind up with an actual vector space, then you've got to go through and check all 10 axioms, at least for now. We'll see in the next section a way to shortcut that in some specific cases.